Hello, everybody, and welcome to this webinar. I'm going to be your host today. My name is Alexander, and I'm working here at Pentalog. Microcontrollers and ESP32 is not my main job here. We mostly do some enterprise level websites using PHP and Symfony. But the world of microcontrollers has always fascinated me, and this became my hobby. So today I will try to teach you a little bit about microcontrollers. A good thing to have would be basic basic programming skills to understand the stuff that I'm going to talk about. But if you're a quick learner, I hope you'll understand anyway. And okay, let's begin. Let me share my screen, and I'm going to show you some slides first. Okay. This we have already discussed a little bit about me and my background. And the main subject, the ESP32 microcontroller. So this microcontroller is rather new to the market. I don't know exactly how long it has been there, but I would say around 2 years maybe. The chip, I don't know if you can see my cursor, this chip is manufactured in China, and it's a more modern version of the ESP8266, which was one version before. And basically, if you ever heard about Arduino, this microcontroller is Arduino-like. And in fact, if you are used to writing code in Arduino, you can do that also using this microcontroller. But for my presentation, I'm going to cover the ESP IDEA Framework, which is the official framework for this microcontroller. One second, please. Okay. So at the end of this webinar, I will share some source code that I made. We will be discussing 4 examples. 2, maybe 3 of them are very basic, and the last example for today is rather complicated. So the last example, as you may know, will be a web server that is used, for example, with a mobile phone or any other Wi-Fi device to run some LED animations, which are colorful and can be used for illuminations. Okay, so a little bit about the ESP IDF. ESP IDF is an official framework for this microcontroller, ESP32. As I said before, if you are used to working with Arduino and the Arduino environment, it's rather easy to connect the Arduino framework with this environment. It's basically an include in your program, and everything should be working fine. But first, let's talk a little bit on how do we set up this framework so we can write some programs, flash them to the chip, see some examples, try out the framework. So to make the whole ESP IDF environment working on my PC or any other PC, I have used Docker. If you're not familiar with Docker, you can install the ESP IDEA framework directly on your PC. It would be nice to have a distribution of Linux, But if that is not the case for you, you can also install it on Windows. The reason that I'm using Docker is because it's very comfortable in a way that all the files related to the ESP IDF and all of my examples are going to be apart from the main operating system on my computer. So again, if you're not familiar with Docker, Docker is something like a virtual machine, to make it easy for you to understand. And basically, this Docker file is almost everything that you need to set up this development environment. And the only difference, for example, for Linux, on Windows, it's going to be a different story. If you would like to install it on Windows, you will need to go to one of the links that I'm going to provide and read the guide on how to do it. But Docker is also available for Windows. So you can install Docker. It's free for personal use. And using the files that I'm going to provide, you just need to run one command and you're going to get the same working environment as I have. Okay, so a little bit about this file. These lines of code, again, if you're using Linux directly, you don't need to input those commands that are in orange. And these lines, for example, they update the system and the packages. And this piece of code, for example, downloads the ESP IDF binaries that you will need to use for the compiling. The main thing here is the compiler, also the monitor software that will allow you to connect to this microcontroller and see a terminal on your screen. I'm going to demonstrate that shortly and see some output from the microcontroller. And this part over here is actually the source code for the whole framework. Okay, so yeah, some useful Docker commands that I'm using. It's docker compose up with the /d, and what that does is it starts the whole container with the framework in detached mode. When I'm finished working, I do a docker compose down, and this basically shuts down everything. And in order for me to run the compile, see the examples, see the serial monitor for this microcontroller in Docker, I need to enter within this container's bash and then run a couple of these commands. Okay, and okay, let's get started with the Hello World example. Let me turn off the presentation and turn on my terminal. So basically, the way I'm doing this from start, I'm doing a docker compose. I hope you can see my terminal. Not sure if the text size is okay. Just let me know if I need to make it a little bit bigger. So, okay, let's do it like this. Okay, so what I do is I do a docker compose upd, and this starts the container with the whole development environment, but I already did that. And after that, I do exec ESP IDF bash, and ESP IDF is the name of the container. And I also have a node container here that I'm going to use for the last example. So we need the one that is ASP IDF. Okay, and then we want to do bash. You know what? Let us do it like this. I'm not sure if the edge of the screen is visible. Okay, so we are inside of the Docker container with the framework, and here it's set up in a way that in this folder that you are going to get, you see a list of a couple of projects that I made. And well, actually, some of the basic ones, I took them from the internet, but they are very simple. But to understand how this thing works in particular, we will discuss them. So what I propose is we start with the very basic example, which is Hello World. Okay, so what I'm doing is I'm entering in this directory, and then, as it was shown on the presentation slide, I will run this command, which is make, and then app, which is going to compile the application for the microcontroller, because it's written in C, and C is a compiled language. And then I can do a couple of these commands in the same row. I can do a flash, and then I would like to run monitor. And what monitor is going to show me, it's going to show me in this console what the microcontroller is doing. And we should see a hello world message also. So as you can see with Docker, when everything is installed, it's as easy as running a couple of commands, and voila, it's working. Takes a little bit of time. It's compiling. And also, while it's compiling the whole Docker installation process, because for me it's already installed, this should take around 10 minutes. So, you know, don't be like, whoa, it's stuck or anything like that. You need to do it once, and after that, it's going to start like it did for my side, you know, quickly. Okay. So I think it's almost done. Okay, right now it's connecting to the microcontroller, which I have right here beside me. I'm going to show it to you in a moment. Okay, so as you can see on my screen, we have a hello world message, which is not coming from my PC. It's coming from this this microcontroller that I have in my hand, you know, the ESP32. And after 10 seconds, it's restarting. All of the messages that you see in green, these are system like debug messages related to Wi-Fi, the processor, and stuff like that. Okay, so this example here is very basic, and let me show it. Let me show how it looks in code, and we're going to discuss a few lines. Well, actually, one more thing, to quit this monitor, because it may not be obvious at first, not like any other console application where you do a Control-C, it doesn't work this way. If I do a make monitor again, I actually need to hold Control and the curly bracket, which is on the right side. And if I do that, I exit this monitor software that I have. Okay, so let me start my Visual Studio code that I'm using to program everything. And one thing to mention here is that I have an additional plugin installed for Visual Studio Code, which is, oh, here it is, Platform.io. It's free, and it's used to, you know, make the development for the ESP32 a little bit easier. Okay, and well, this is a rather complicated example that we're going to cover in the end, but let us start with hello world. So in any C program that you may have seen before, to use some of the functions that we have, we need to do a couple of includes. And okay, one second. Okay, so the main entry point of the program is the function which is called app main. This is by default always the case. So your program is going to start at the beginning of this function. And here it's very simple. We just do a printf, which is going to output this string into the console. And we should see a hello world message at this point. Additionally, here, to make this example a little bit more interesting, we are displaying some of the chip features which this microcontroller has. And in order for us to do that, we declare a special type, which is ESP chip info. This is the name of the variable. And we are passing this by reference. So what we do is we actually input a pointer to this variable, to this function, in order for it to populate it with the data that we require. And one question that you may ask at this point is, okay, so how do I know what this is, for example? And the answer to that question is that there is some official documentation for the framework, but it's generated automatically. So from what I have seen before, from what I found, the best way is to look into the source code. And let me just start my browser real quick, and I'm going to show it to you how I do this. So we need the ESP IDEA at GitHub. Okay. So this is the repository for the framework. And what I do is I enter here and paste the name of the function and do a search in this repository. Okay, and this first result from the source code you can see here that it's a structure. In C, a structure, if you have a programming background, you're probably used to objects. And the difference in C between, we actually don't have objects in C. We have objects in C++, but we are writing in pure C. So the difference between a structure and an object is that the object has a couple of methods, and the structure, on the other hand, has no methods. And the structure, you may think of it as a type, a container that holds other types that are, for example, more primitive. So this type, for example, has an integer, a number, which corresponds to the number of cores that this microcontroller has, the number, the revision, well, the version of this microcontroller chip. It's a bigger integer, which is its features, and another structure inside that is related to the model, but we're not going to look into this. The idea is to show you how you can look up some functions that you will be using. Okay, so here in this example, so what we did is we declared a variable with this type, and we have populated with some data. And basically what we do next is we input the %d, which will be using this value. The number of cores should be 2, if I'm not mistaken. And we do an AND, which basically means does chip features contain within them this constant, the chip feature Bluetooth, and also does the chip info features contain another constant, which is feature Bluetooth E. Not sure what the difference is between the BT and the BLE, but I think a BLE is a more advanced version of a Bluetooth device. Okay. Also, the revision of the chip. Its flash size from the looks of it, it's a byte. Okay, so yeah, if we divide it by 1024 times 1024, we should get the size of the flash in megabytes. And then basically we do a for loop, which is going to echo 10 times, restarting in the number of seconds. This particular function is very interesting. We're going to cover it in the next example, but just so you know why the ESP IDF is so special. because actually inside of this framework, when you compile and flash it to the chip, there is actually an operating system running inside this chip, which is free. The name of the operating system is FreeRTOS, which is operating system used. It's an open source operating system, and it's used in a lot of modern microcontrollers. And this special delay is used because inside FreeRTOS you have multitasking. So what we're going to see in the next example and in the following examples, that you can have a couple of tasks running. So for example, let's say you want to blink a red LED and you want to blink a yellow LED at the same time. So without the multitasking feature of this operating system, that would be something hard to accomplish. And for example, there is on the standard Arduino, there is no such thing as an operating system, which makes the ESP32 a more modern microcontroller that you would like, to use for more complex projects. Okay, so yeah, that's all for this example. And before we go to the next one, which is the blink, I would like to talk a little bit about the chip itself. My boss for today's meeting is telling me that I have some questions. Let's see. 1 second. Okay, an interesting question here is where do you get the Docker file? At the end of the presentation, you're going to receive an email, and there will be a link to my repository and to this version of the Docker file that I'm using. It's basically, it's made by me, and you're going to get a link to the repository at the end of this webinar. Okay, so one of the people is saying that BLE is a Bluetooth low energy extension profile of Bluetooth. I didn't know that. Thanks for the info. Okay, so a few words about the chip that I was going to say. So here is the picture of the microcontroller that I'm using. And the main thing in this board is this chip. It's developed by Espressif Systems. This is not the official version of this board. I'm using a Chinese clone. The microchip itself, it's made in China anyway. And I'm basically doing this because it's around $4 compared to the original version. And it's pretty much considering that the chip is made by the same manufacturer, it has the same features. This thing on top is the antenna, which is used for Wi-Fi and Bluetooth. This chip here is the flash memory where you store your applications, and it's apart from the main chip. But there are like 4 different modifications of the ESP32 chip, and I think one of them has the flash inside of this chip, so you don't need to use a separate, flash component. This thing here is the converter, which is used to communicate with the USB. You can see a micro USB jack here, and by using this this component, it's communicating with the main processor. Also, on my version, you can see a connector which is used to connect batteries to this board, and you can connect the battery, and it will also do, I think this chip, it also does battery management. So if you connect a lithium polymer 4.2 volt battery, it's going to handle the charging and discharging for you, not to damage the battery. Also, the chip has an LED that we're going to flash at the moment in a short while, and this LED, it basically indicates that there is a communication between the microcontroller and the USB. So when I'm flashing the software, I always see this LED blinking. Also, there is another version of this microcontroller, which I don't have at the moment, but the same chip and memory is here behind this metallic plate. Basically, the difference is that the metallic plate is used to, cancel some of the noise and the interference that the surrounding environment has. Also, from what I've seen, there is a version with a special connector here, which you can, it doesn't have the internal antenna, but there is a special connector here, which you can use to connect an external antenna to increase the range of the microcontroller if you need it. Okay. Okay, some questions here real quick. What OS are you using at the moment on the ESP32? So, like I said before, I'm using the official framework, and this official framework has support for the FreeRTOS operating system. So the OS is FreeRTOS. What is the value of the config minimal stack size? 60. I'm not actually sure, I haven't checked, but from what I know, it's the minimal size of the stack that you need in bytes for a single task. So you cannot go less than that. A good idea would be to check the documentation if you're interested. Personally, I haven't checked. When I don't use this constant, I use something like 1024 or 2048. Maybe if there is time, you can give us your thoughts regarding FreeRTOS. Have you considered using MicroPython? Okay, so yes, I have been using MicroPython, but I haven't been using it for this microcontroller in particular. I have been using it for the previous version of expressive microcontrollers, which was ESP8266, which was very popular. One second. From what I understood, from what I saw, the MicroPython was kind of nice, but at the moment it was still buggy. And frameworks like Arduino, they're also very nice for beginners, but if you would like to go into the details of how all of this stuff is working and maybe, learn something a little bit advanced, I would definitely consider looking into ESP IDEA and the FreeRTOS. But if you are a beginner, maybe it's a good idea to work with Arduino. because there are a lot of examples on the internet that you can find, and it's a little bit more simpler than the stuff that I'm showing today here. The stuff that I'm showing, it's rather more advanced. Okay, so those are all of the questions I saw before. We're actually excuse me, limited in time, so let us check the second example. And the second example would be the Blink program. Okay, someone asked to do a full screen on my editor where I have the code. Okay, so in my terminal, I'm going to go into the Blink application. Okay. Let me flash the software to the microcontroller. We won't do a monitor because there's nothing to see in the console for this particular example. Okay, so just to let you know that it's working, I'm not sure if that's going to be visible, but this is the microcontroller, and the blue LED on top is flashing. Okay, so we know that it's coming from the microcontroller device. Okay, and let us explain the code a little bit. This make software that I have here also has a special command, which is menu config. Okay, and here on the screen right now you see a special kind of menu, which is like a BIOS, similar. It's not a BIOS on your PC. It just looks similar. And here, for example, you have a lot of options. You can enable Wi-Fi, enable Bluetooth, enable additional debugging and stuff like that. But the thing that we're interested in here is this. So, for example, I have my LED, which you just seen flashing, the blue one, connected to pin 22. And on other versions of microcontrollers, you may have the LED connected to some other pin. Or maybe you would like to, for example, right now I'm using the internal LED that the microcontroller has. For example, you would like to connect your own LED that you may have to any other pin. And in order for me not to edit the source code, the ESP IDEA framework provides a possibility of creating these menus, which you can use for configuring your project. And basically, to create something similar, here is a short example. So what this does is actually it creates an additional option in the main menu that I have just shown you. And here you would be able to input a pin number that you would like to use for flashing, you know. And this file is also part of the ESP IDEA template, which I'm going to link at the end of this webinar. So whenever you're making a new application, you don't need to create all of those files. You have already made template available on GitHub, which you basically clone and you start developing your project. So this file is part of that template. Okay. Let us talk real quick about this example. So as we said before, app main, the entry point of the application. And here, as you can see, we are creating a separate task, which will be used to blink the LEDs. For example, if I had more than one LED embedded into this microcontroller, I could create like 2 or 3 tasks that would be used to blink those LEDs separately. And here we are passing the name of the function that is going to be executed. This is just a name. You can input whatever you like in here. This config the minimal stack size, again, that we have discussed. Here, this is basically used to pass parameters to this function if you need any. In my example, it's not null because I'm not going to pass anything. This value here is the priority that is going to be used for this task. For this example, a value of 5 is okay. The highest priority that you can get from what I understood is 1. Also, it's worth mentioning that app main is a task itself. It's also a task and it has its own priority. But inside this task, which is the entry point of the application, we're creating another task. And the last argument here is used to get, if you pass a special type of variable here, you will get a reference to this task. And this reference is used to, for example, disable, delete, pause this task outside of this code. And if you would like to disable the task within this function, there are other variants. And one important thing about this task within the FreeRTOS operating system is that these tasks they don't end. Okay, so here you can see an infinite while loop. So writing a return here at the end would give me a compile error. So the task has to run forever. If you want to delete it for some reason, you need to do a vtask delete inside here. And as a reference, you need to pass null because you are already inside the task. And here, if you have the reference, you can use the same function, but as the parameter, you need to pass the reference if you want to cancel the task outside of the code. Okay. So just real quick here, GPIO pad select, blink GPIO, and this is actually the value that we gave in the configuration menu. In my case, this is 22. And this function is used to reset all of the pins that the microcontroller has. As you may have seen on the picture, this microcontroller has a lot of pins, and they can be used for various stuff. And the basic functionality of this pin is that it's running like a GPIO. GPIO stands for General Purpose Input Output. And in order for any pin to be working as a GPIO, which we need in this example, we need to run this function because this pin may be configured to be used for in some other mode. Okay. So for every pin inside of the program, we need to do a GPIO pad select and input the number of the pin. Okay, in this example, we are flashing the LED. So in order for the LED to flash, I'm just going to show the schematics of this example in a moment. We need to provide the number of the pin and use this special constant to make it an output pin. If we make it an output pin, it can provide current to the LED. And if we do a 0, GPIO set level 0, the LED is not going to work. Then we do a delay for 1 second. Well, actually, the delay function takes as the parameter the number of ticks that it needs to wait. But we have this constant inside the FreeRTOS, which basically is the value of how many ticks is 1 microsecond. And by doing this division, we get an effective task delay in seconds. So after we have waited for 1 second, we do a GPIO set level number of the pin 1. And at this point, the LED will light up, and you're going to see it on your board. And after that, we do a v-task delay. We wait for some time, and this cycle continues and continues and continues. And the LED is flashing. Okay, let me quickly show you this example. Okay, so this is the diagram of the schematics of the blue LED flashing. The only difference is that my LED is actually connected to 22 instead of 29, but it doesn't make much difference for this example. You can use any other pin number if you're connecting an external LED. If you're using the internal LED, it's from what I have seen, it's mostly located on pin 22 for this microcontroller, but there may be other variants where it's situated on some other pin. Okay, so this is the LED on the schematics, and this thing that I'm using here is a resistor. The microcontroller cannot provide a lot of current. From what I understand, the ESP32 can provide up to, let's say, 30 or maybe 40 milliamps of current. And in order to, for the microcontroller, so you don't burn this pin, you don't break it by accident, you need to always put this resistor here. In my case, it's a 100 ohm resistor. Okay, so let's see if we have some questions. Okay. What I would like to show you next is let's discuss real briefly the pins that we have here. So if we are talking about, well, you cannot use all of those pins because some of them are used to power the device. For example, ground and 3v3. Here you give the positive from the battery, and here you give the negative. Also, you can use the USB port if you like to power this device, or most of the other pins, apart from the 5v1 and this GND, which stands for ground, you can use as general purpose input-output pins. Okay. So when we are talking about GPIO pins, you basically have two options. You can configure a pin to be an output or an input, and let's discuss a little bit what's the difference between those two types. Okay, so in the example where I just flashed an LED, the pin was configured as an output. So whenever I configure this this pin as an output, like for example here, pin 21, okay, so this code is used to reset the pin. We need to always use it if we want to use a pin as a GPIO. And for example here, the pin 21 will be used in output mode, okay? And then we set a level for this pin to 1. Which would effectively mean that on pin 21, you're going to get a positive voltage. Just the same as here, okay? And if you would do on the next pin, which is 24, if you would do a GPIO set level 24.0, you would get a minus, a minus, which is the same as the ground on this pin. Hope this makes some sense for you. And the other mode which can be used for the GPIO pins is the input mode. And what that means, if for example we're configuring the pin 27 as an input pin, and if we are connecting it using a resistor, you know, not to burn the pin, not to break the device. If we are connecting it via resistor to ground, okay, and use the special function to read the level of this pin, we're going to get a 0. Okay, if it's connected to ground, you're going to always get a 0. On the other hand, for the pin number 30, if we connect it to the positive voltage here, when we run this function, we are going to get a 1. So as the word stands, output is used to output current, and input is used to read current and say whether there is current present or there is no current present. Okay, right now let's, I'm not sure we're going to have time for the last example. I'm just going to show it to you real quick briefly, and if you're interested, you're going to have to check out the source code for yourself on my GitHub repository. But we have some time to really quickly cover this example, which is a traffic light. And I cannot show it to you on camera, but I have prepared a video. Okay, so here is the traffic light example. It's something a little bit more advanced, where we use one pin as an input, using which we're going to detect the press of a button. And those 3 other pins are used to light up those 3 LEDs. All of the pins have resistors. And basically what this does, it's working like a traffic light. And whenever I press this button, once it's once it's green, it's going to, so here I'm pressing this button. It's going to turn on in yellow and then in red. So effectively, if we would be talking about a real traffic light, this would be the situation where I press the button and I can cross the road. Okay, and this is the schematic for this example. You can see that we have 3 LEDs connected. All of these pins will be configured as an output, and only 1 pin will be configured as an input. And here we are also going to be using a pin and input mode, but we're also going to set a special mode for the input pin, which is input pull up. And this needs to be done in order to cancel the noise which is coming from the environment. So in order for us not to get false triggers, and we want to, you know, the lights to work only when we actually press the button, we will need to use a special mode for this GPIO. Okay, let me show it to you real quick because we don't have much time left. Okay, traffic light. Okay, here's the source code. Here I'm demonstrating the basic concept of how information inside FreeRTOS is transferred from one task to another task. We have a special function here on top, which is called interrupt. And what this basically does is the main program is running inside this task, okay, which handles the flashing of the LEDs. So inside the app main, here in this place, we're running the task which basically flashes those LEDs. But the functionality that we would like to receive, that we would like to get, is whenever I'm pressing a button, I want in any scenario, I want the green LED to stop flashing, and this is why we need an interrupt. And the interrupt is a special kind of function which gets executed at any certain scenario that you provide. In our example, when this pin is connected to ground, like I showed you before, it becomes a 0 when we try to read the value from it. When we get a 0 on this pin, what we would like is this function to run, you know. And here we are using a special type of data, which is called a semaphore, a binary semaphore. And basically what it does is that it's going to receive the data that we're going to take in the main task and decide whether we need to flash the yellow light and then turn on the red light, or we continue with the green light, with the main procedure, the main principle of how the semaphore is working. Okay. And again, these are the pins that are used for the 3 LEDs and the button. We reset them all to be GPIOs, general purposes input-output pin. We set a direction for the button pin. We're making it an output. All other LEDs, an input, and all other LEDs pins are outputs. Okay, and we enable a special mode for the button pin, which is GPIO pull up. And what that does is, by default, if we try to read its value, it's going to give us a 1. And this is to cancel the noise that is coming from which is the interference from the environment. And only when we are connecting it to ground by means of the button, it's going to trigger the interrupt. Okay. So here we are attaching an interrupt, the special type of function which gets called when we press the button. Okay, and we say that we want to this function only to run when the level of the pin is low. Okay. This is also a configuration function for the interrupt. And here we're effectively attaching this function to this button whenever it's 0. Okay, so here the logic is very basic. It's basic. It does delays, it flashes LEDs, and switches from one state to another. But the important thing is here, which is X semaphore take. So when we have pressed the button, as you've seen on the video, that special function of mine got executed, and we gave something to this container which holds our value. And when it has a value, it basically means that we have pressed the button. Okay, so again, in this code here, whenever I press the button, the result of this function is going to be equal to PD true, which is some kind of constant but for us it basically means true. And then we do a printf button pressed. We turn off all of the LEDs, and then we start flashing the yellow LED like you just have seen on the example. Okay. So we're very short on time, but real quickly, the main application that I was going to show to you, which is using these LEDs, which is a JSON API web server. Let me just quickly run the video for you. Okay, so those LEDs that are controlled individually, on this video, I'm effectively controlling them from the ESP microcontroller, which can, use a special kind of protocol that is used for these LEDs, for those LEDs. I have a web server. This web server, what it does, it gives my cell phone a special JS application like a website. And I can use this application to control my LEDs the way I want. Okay, and so it has. I've made like I don't know, like 6 or maybe 8 different modes for those LEDs, and those LEDs I will actually be using them to automate my own home. I'm going to buy a really long strip of those LEDs, and I'm going to hang them on top of my ceiling. Okay, and just a quick pick on how the application that I'm running on my mobile phone looks, as it looks something like this. And whenever I click, I can change a particular mode. Okay, so for example, for the color white mode, I can choose a color. I can also set the speed and configure the brightness that I want. Okay, so again, this example is a little bit more complicated. It uses Wi-Fi, it uses JSON, it uses a web server, and it uses a special protocol to control the LEDs. Sorry, but we didn't manage to fit in into 1 hour. Let me spend some time real quick to answer some of your questions. I have one new question here. If you had a bit more time, it would be nice if you could tell us what future projects are you working on or thinking of. I'm actually thinking of using a special kind of screen to make a clock for my home because I just bought a new apartment, and the one thing that I don't have at my apartment is a clock. So I would use a big LED screen, which just has one color red, to make a clock that I'm going to control with Wi-Fi, and it's going to use it's going to work on the ESP32 microcontroller, and I'm going to connect a temperature sensor in order for me to know what's the temperature inside of my room and what's the humidity level inside of my room. And it's also that clock that I'm going to build. It's also going to synchronize time through internet. Let's see if we have some more questions. Why are you not using the Arduino IDE? Well, because at this point, what I would like to do is I would like to learn something beyond the Arduino IDE. Arduino IDE is very nice. I've started learning microcontrollers with the Arduino IDE. And I also one thing that I still don't know is the C programming language. So in order for me to learn it at full extent, I've started using something different, something apart from Arduino. The Arduino IDE, the question was, is the Arduino IDE included on the Docker image? So no, the Arduino IDE is not included on the Docker image, but you're going to receive my presentation, and there you have a link to a website, which is ESP32.org, and there you will find a lot of tutorials, a lot of basic tutorials, and a lot of more advanced tutorials on the subject. And there is also a step-by-step guide there on how to use Arduino with this particular microcontroller. In terms of security, have you got any advice? Well, yeah, use a long password. Password protect your Wi-Fi network. And with this, basically, it's all of the security that this device has in terms of Wi-Fi. So you just use a password. You could try Home Assistant on Raspberry Pi 3 and ESP home lib to flash the ESPs, best of both worlds. Yeah, I actually have a Raspberry Pi, but I'm mostly using it for gaming. But it's also a good idea to check what the Raspberry Pi has to offer. And I quite like the concept of OTA update for microcontrollers, which means that basically it updates through Wi-Fi, you know, and you don't need to use wires. Did you use ESP32 to connect to Azure Cloud by using MQTT client? No, I have never tried MQTT and Azure Cloud. Maybe that's something that I'm going to try in the future. Okay, guys. So as I can see, those are all of the questions. One last question from Daniel. Do you plan to do a similar presentation for VMAS ESP8266? Well, not at the moment, because I did use the VMAS ESP8266, but when I saw that they're going to release this new microcontroller, I have decided to use this model for the presentation. From what I can say about ESP8266, it practically uses the same functions and the same environment. So again, on this website that I'm going to share with you, I didn't do that website, but it's a great community there. And if you're interested in the previous version, which is ESP8266, you will learn something there. Okay, guys. Sorry we didn't have the time to cover all of the aspects. This subject is quite vast and quite interesting. What I would like to say that at the end of this webinar, you are going to receive an email where you can provide feedback for this webinar, and also you're going to receive my presentation, the source code of the projects that I was showing, and a video recording of this webinar. Thank you very much. Have a great day.